So hi everyone, today we have a talk by Anna Bickel. She's a bachelor student in physics and she will talk about application of physics to the field of medicine. So please welcome her.
Oh, hello everyone and welcome to my talk, which is about applying physics to medicine, and the application we're going to look at is the standardized structure naming, which is the holy grail of radiation therapy. And today we are going to first look at some theory which you're going to need to understand radiation therapy and standardized structure naming. And this whole application was my bachelor thesis in physics at the Proton Institute at PSI. And yes, so I would like to start with the question, what is medical physics? And I really like this definition by the Nyson's Medical Dictionary from 1814, which is that it's physics applied to the knowledge of the human body, to its preservation and the cure of illness. It seems like a really bold statement, but it is really what we are trying to do. We are trying to cure illness and still preserve the body. And you might think that medical physics is a very new science, but it's actually really old. It has been included into the Royal Medical Society of France since 1778. And the first application, which we would attribute to medical physics, has been traced back to 2500 BC. So it's old, but we only call it medical physics for around 300 years. Now, medical physics today has many applications, and we will look at them. So we have radiation therapy. This is where we apply radiation to cure cancers. In diagnostic radiology, we use any type of imaging to diagnose diseases and ailments. So we can image a tumor, but we can also use an X-ray to look at broken bones. So it's not only to look at tumors, but also very simple things. Nuclear medicine is where we are one step ahead, but okay. So nuclear medicine is where we use radioactive tracers to look at developments in the body. So we can look at how a tumor develops or how much sugar a tumor absorbs using radioactive isotopes. In health physics, we concern ourselves with radiation limits, and it concerns several government bodies. And we define radiation limits for the general population, but also radiation limits for occupationally exposed people. So it's not only medical physicists, but also people working in nuclear power plants or radiation specialists. Medical optics is where we use physical principles to look inside of the body. And the easiest application is an endoscopy, where we look at the digestive tract or even your nose or your everything. We use medical optics. And the last thing is biophotonics, where we use fluorescence microscopy to look at cells and tissues. So medical physics is really broad, but today we will only look at radiation therapy. And radiation therapy, its definition is that we treat disease through radiation, and we will look at a typical workflow in radiation therapy. The first thing we always need is an image of the tumor. So we need to know that there is disease to treat. Here we can use CTs, MRIs, but also PET scans. If you're not familiar, PET scans are positron emission tomography. We use a radioactive isotope which decays into positrons, and then we measure those. When we have the image, the doctor delineates the target. So the doctor delineates the tumor, and such that we then know on the CT as medical physicists where the tumor is and what we have to plan. Then we go into the actual treatment plan development, where we have to develop the treatment to define where we depose how much radiation and everything that is needed to know. And when we are happy, we first have to evaluate the plan, so we have to test it, not on the patient, but on different testing devices, and we have to be really sure that the plan is what we want it to be, because we don't want to accidentally give too much radiation or too few. Then the plan delivery is where we deliver the plan. Quite simple. The patient comes in and gets irradiated, and every day the patient gets a daily image, so a CT or an MRI, and we look at the tumor before we irradiate. And if we see any big anatomical changes, so if the tumor shrinks or grows, we can adapt the plan such that we really do cover the tumor and not just miss it because something changed. And yes, we need to look at tumor and target volumes. So the tumor is the site of malignant disease, which you probably have already guessed. And during treatment planning, we have to define different target volumes, which help us to... okay, this thing has a timer, but I don't know what to do against it, so we are running against the clock. Wait, maybe I can... Can I? Okay, I've paused it. Maybe it's going to let me speak. So the first volume is the gross target volume, which is the visible tumor on the image. So it's just we mark on the CT where we see the tumor. This is what the doctor does. Then we have the clinical target volume, where it's a margin added to the GTV to make sure that we do cover the whole tumor, because we have cancerous cells which are around the tumor, which we do not see in the image, but we still have to kill them, because if we don't, the cancer will come back. Then the internal target volume is the first margin we add as medical physicists, which is that we make sure that if the tumor has any anatomical change, so if it grows or if it shrinks, that we still cover the whole tumor during radiation. And the last volume we add is the planning target volume, which is the last one we as medical physicists add, which is to make sure that if the patient is not situated exactly the same way as in the planning CT, because it's basically impossible to lie exactly the same every time, that we do cover the tumor. So if we are shifted a bit from the actual axis which we want to be, that we cover the tumor. However, the problem is in the PTV and also in the ITV, we only have normal tissue, so no cancerous tissue, and we want to keep those two margins as small as possible to not kill too many healthy cells, because those help in the cure of and the repopulation of the killed cancer cells. And target delineation is when we contour and label these volumes on the planning CT during the planning process. And we have to categorize these different targets into different groups. We have primary tumors, which are the first or the original tumor in the body, which is pretty clear. And then we have nodal targets, and these are metastases of the primary tumor. And the metastasis is a tumor which has the same histology as the first one, so it originated from the first one. And we have to treat all of them because we need to eradicate the whole cancer. So we also, when we plan, we need to somehow know which target is which one. And so we have the multiplicity of targets, and the multiplicity is not defined in a mathematical way. It's just you count the number of targets, and the primary target is mostly number 1, and then all the nodes are 2, 3, 4. So it's just numbering. And we also need a definition of dose, because we need to treat the tumor in one way. And we use the definition of the physical absorbed dose, which is the average energy absorbed per unit target mass. And the unit is 1 Gray, which is 1 joule per kilogram. And on the right, we have depth dose curves for different particles. And you can see that not all of the particles deposit the energy at the same depth and in the same way. And all of these particles can be used for radiation therapy, and you may imagine that every particle has a different use. For example, the electrons and photons, they deposit most of their energy at the beginning of the body, but then the protons and the carbon ions, they have more of a peak where most of their energy is deposited, and then afterwards we have almost no energy. And this peak is also called a Bragg peak, and you can see that depending on where the tumor is or what exactly we're trying to treat, different particles may be useful. If we treat a skin cancer, we would mostly use electrons or photons, but for brain cancers in children, we would use protons. So every particle has its use, and it's always figuring out which one is going to be the right one. Now, I've mentioned that we have healthy tissue, which we also irradiate because we can't really just pinpoint all of the radiation to the tumor, and there are 3 different types. We have the organs at risk, which we abbreviate with OR. These are organs which are sensitive to radiation, basically every organ you know in your body, like the lungs or the heart, or even if you have a brain tumor, the rest of the healthy brain is still an organ at risk because we don't want to kill more brain cells than needed. Then anatomical structures are sensitive normal tissues, which aren't necessarily organs. I put the example of an optical tract, but any nerve, any artery, anything like that, which is important to the bodily function, we do not want to irradiate. So we need to be aware which ones we have. And the last is medical equipment, which is not an anatomical structure, but it's something inside or on the body, which we do not want to be irradiated. Examples would be an ostomy bag or screws. A lot of patients have surgeries before they come to get radiation, and you fix bones with screws a lot of the times, and we do not want to irradiate those screws because then the bones wouldn't grow back. And now, for this presentation, we are going to call all of them organs at risk, so OR. And you will see in a moment why it's important to group them all together. So we will look at this mess of a slide, or basically this mess of data, because this is where I started my semester project. And you will see I've grouped all of these names and strings in different colors. And you might have already guessed, the blue ones are all target volumes. You might have recognized the PTV, CTV, the target volumes abbreviation. But even if we look at these strings, most of them you will ask yourself, what do all these numbers mean? These characters, what are they really labeling? It's already quite difficult to know. Then the purple ones are organs at risk. Some of them you might have guessed. If you know a bit of German, Tränendrüse and Sehnerv are obviously organs at risk. But then we have the LOCGL, which, who knows what that is? I mean, you look at it and it's not clear what it's telling us. And the last group are the red ones. They are red for a reason, because we don't really know what they are trying to tell us. Some of them are just strings of characters and numbers, and it's without any information, it's really difficult to know what they're telling us, or some of them are not even really useful, like labeling that there are multiple metastases is not really as useful as just labeling the metastases. So to solve this problem and bring some order into this chaos of data, we want to develop a standardized naming convention. So this is now our goal. And the project scope is that we first want to find a standardized naming convention, not only one, but actually 2 of them, one for the target structures and one for the OR. And there is a reason why we want to do this, because we want to retrospectively standardize all of the names that were given. And in the first step, we want to standardize all of the names at the Proton Institute at PSI. And when I worked on the project, I had data spanning from 1980 to 2024. So we have already over 40 years of data, which looked like the examples before. So if any researcher wants to find something useful in these over 40 years of data, it's going to be really difficult if you don't know what you're looking for or what you found when you look something up, because you don't even know what it's trying to say. So for gathering any data for research, or also giving research data from PSI to other institutes, we have to have some sort of common understanding of what all of these names are. And if you're familiar with any programming or automatization, you know that you always need a standardized convention, not only for names and strings, but any automatization needs a standardized convention. And here we had the idea of not only retrospectively convert the names, but also prospectively convert the names. So we would implement a template-based treatment planning. So when the treatment planners would name their structure, they had a template, which would give them feedback if the structure coincides with the convention, but for that you need a standardized convention. So not only do we want to find a standardized convention, but we want to implement a code to convert these names. And we will look at the convention and the conversion of the code at the same time. So on the left, we will have the steps which correspond to the convention, and right we have an example which will show how the code converts it. And I have to preface this that we wanted to find a convention, but then we figured out that there wasn't any. So instead of finding one and using it, I had to first develop two conventions. So these two conventions, which you're going to see, are new conventions. They do not exist anywhere in this form. And then also write the code to implement these conventions. So we will start with the example up there. And the first step for the targets is we have to find the name stem, so the target volume abbreviation. So here you might have guessed it's PTV. So we write PTV uppercase. The next thing, we have to identify if it's a primary or a nodal tumor, and we abbreviate it with N or P. So we add an N, a small n or a small p here. We see the N, which probably indicates that it's nodal, so PTVN. The next thing is the multiplicity, because if we know it's a nodal target, it should have a multiplicity of at least 2. At the end, we see the 3, which indicates it was the third target in this patient. So we add the 3. And now everything which we are going to add afterwards is going to be added with an underscore in between to make it more readable. The next thing we want to identify is the location, and in the first step, it's only if the tumor is on the left or the right hemisphere of the body. So it's not any other location information, but only left and right. And in the example, we have an R, so again, we add right. We have a list of permitted additional information, which I'm not going to show you, but we figured that treatment planners were to name their targets anything. You couldn't imagine what I found for weird names. So we have a list of positional arguments and also extra arguments, like if it was a pre-op tumor or a post-operative tumor, things that are important can be added. Here we have the additional position information that it's located upwards of something. I don't know, but it's located up, so we add the up as additional information. Now, the next thing is the dose, and we add the dose in centigrade, just to not have any decimal points. And we have 6,900, which would mean 69 gray, was delivered to that tumor. So we add it. And the last thing we want to know is if the target volume was expanded. So when we plan, you first draw a delineation, but then you might see, oh, but I actually have to cover more space than I thought. So if you expand it, you can add it, and it's added in millimeters, again, just to have no decimal points. And I mean, the body's not so big, you don't have, if you have brain tumors, it's not really that big, so millimeters makes sense. And here we have the 0.5 for 5 millimeters. So now you see we started with that, and at the end the code will give us this converted name for the target. Now the same happens for the ORs, but it's a lot shorter. And we have my favorite example, the log-G, to look at. So first we match the OR to a name stem, and the name stems come from a list from the AAPM, which is the American Medical Physics Society. They made a list of organs at risk, and their list includes all of the ORs like we defined them before, so anatomical structures, medical instruments, but also organs. And we have 700 names they defined, and then there are more names that I had to define which weren't on the list. So these are also new. And log-G is the lacrimal gland. These are glands in your eyes which produce tears. And you can also see the name stem is considerably longer than in the targets, but we try to shorten it in a way where you can still understand which target it is, but to not make it unnecessarily long. Then we identify the location. Here we identify first, again, left and right, but then because in organs we know where they are, or muscles, or all of these things, so we also definitely know if it's inferior to something, superior, up, down, left. So you know the position more clearly than with just a tumor which is somewhere in the brain. So here we add the L for left, which was also before. Then you could have permitted additional information, which again follows the same idea of some special positional arguments, but then also technical structures or anything else. Here we actually do not have any. So you can also see that even if a name doesn't have one, it will not just randomly add something, but we have to have the option for people to put additional structures in, but additional information in, but it doesn't mean that it's needed. And the last thing is that we identify again the expansion of the volume, and we add it with PRV, and PRV is the planning organ at risk volume. It's just to indicate that it's an organ at risk and that it was expanded, and just to make sure that it's more or less compatible with the target convention. But of course, you can see the names are quite long, and we did not impose a character limit for the names, but we tried to make them as short as possible. So, for example, the locations in the OR convention are shortened to the first letter or the first 3 letters to make the name not infinitely long. And so I think some examples would be good to see what the code can do. So I defined new OR name stems, as I told you. And these were just things that weren't on the list. The first is a palatine nerve, which is a nerve in your brain, which will be then abbreviated to nerve palatine. So you see the abbreviation for a nerve is NRV. Quite simple. The pharyngeal constrictor muscles is a muscle group. We have a common name stem, and then this is a place where you would add, for example, inferior or superior, because we know which one is the superior pharyngeal constrictor muscle. So here you see where the location would then come in, and then a catheter. We have a lot of patients, if you have like prostate cancers, they would have catheters, and somehow this was just not on the list, so it was added. And then some converted names that might be interesting. We have the basilar artery. There you can see we add an A to indicate artery. Submandibular gland, which will be gland submand. And then we also have some target structures. And there you can also see the tech PTV. So there exists something as technical target structures, which just are structures that were defined during the planning process, but are not really something we are going to irradiate. But they are still labeled, so there is a possibility to add tech in front of any target volume if needed. Now, I've talked about code, so I will just give you a structural overview. I will not show you any code because that would be really boring. And we start with the data set we want to test. We will sort them first into target structures and then non-target structures, because as we have seen, there are 2 different conventions. They have to be converted differently. We carry out the conversion, and then we test and see if they are correct. So they could either just be wrong, which happens, so nothing really happens. We just retest the word at a later stage again. We have correctly converted names, which is great. And we do not do anything with them. And then there is the not converted names, which are just things like the CZ Tech, which we just decide to not convert because they're either not useful for research or just not useful structures, or we just don't know what they mean. So there is a point at which you have to draw a line of what you can convert and what you can't convert. And at just a string of numbers which doesn't says anything, we drew the line of, yeah, that's not going to happen. And We do a ground truth data set, which is a JSON file with a dictionary, where you have the converted name, and then all of the names that were converted to it. So you could have PTV plus 4 millimeters, but you'd be astonished there are like 7 ways of writing that. So it still will always be converted to the same name, but it has like different translations, I guess, which were the original name. But they were all a PTV expanded by 4 millimeters. And that ground truth data set is quite big, and you just add new words when you add the correctly converted words, and the not converted words will also be added. There's just a list of not converted and then any words, and if you want at a later stage to convert these names, you then easily can find the ones which weren't converted. So if you talk about code and converting things, we should probably talk about how accurate this whole thing is. And we calculated the accuracy, and for the target structures, we have a very high accuracy of 99.36%, which is very good. And for the organs at risk, we have almost 95%, which is also really high. And we have the ground truth data set, which I talked to you before. There are over 8,000 converted names, and yes, I did convert all of them and check them all by hand. That's just something you have to do at the beginning when you write a conversion code. I added 60 new OR name stems, so I had to create 60 new name stems which weren't on the list. And I created a dictionary, which is something I didn't talk about yet, but we had German and Latin words, which, as you might have guessed, the convention is in English. So if we have a German or a Latin word, it won't be converted, because how would the computer know that it's another language? And also there are cases where we need synonyms. So you have like the stomach, you could just call it stomach, but there are also other names which doctors use to call different organs, and these can also not be converted because we only have one name stem and you match it to the existing name stem. So we will just look quickly at the German and Latin dictionary. So first you have to translate these words and find their corresponding name stem. You can then add, so there's a dictionary which decodes when it happens to come across something that cannot be converted. It will then go and check if the name has to be translated first, and then it will carry out the conversion again if needed. And some examples which are quite funny, or at least nice to look at. Gaster, which is the Latin word for stomach. We have Auge, Tränendrüse, which would be the nasolacrimal duct, and Sehnerv, which is optical nerve. So you see, we find these correspondences, and then the code can go and look up the translation. Now, there are always things that are difficult to convert when you have a code or strings. And the first thing are special characters. In general, I mean, you know, if you name a file on Windows or Mac or Linux, you can't use every character in the file name. It will just, if you put a special character in, it will probably tell you, no, please don't do that. And that's the same with commercial treatment planning systems. You can't just use any character. So you might have gathered that we only used an underscore, and that's the only allowed special character. And also matching these characters as strings in Python is quite annoying. It's not something you can't do, but it would just be easier to not have any special characters. The next problems are umlauts. This just stems that the data is, we have so many years of data, and in the 80s and 90s, the treatment planners did the treatment plans in German, so all of these structures are named in German, but our convention is in English. So this is one of the problems, and the other thing is that umlauts are hexadecimal characters, so instead of just writing normal strings, you have to first look up the hexadecimal code, put it in, and then match the string, and make sure that it's always correct. The next thing are dates, and you would probably wonder why on earth is a date such a problem. if I look at it, I know it's the 9th of April 1980, but if you are just a code, a computer, you might look at 1980 and wonder, is it the year 1980 or is it just 19.8 gray? Or the 9th could be the 9th of April, but it could also be the 9th target. So this just makes the whole thing more difficult because at the end of the day, you're working with a machine and the machine only is not a human. So if I have a difficulty identifying if it's a date or not, imagine what the code is going to do. The last thing is location descriptors directly at the end of the OR name. So the example would be lens L. And here the thing is it a typo or is it a location? It could be the left lens of the eye, but it also could just be an L which the treatment planner randomly clicked on. And if I can't say with 100% certainty that it's the left lens, then obviously a code can't either. So in general, we would like to have consistent name stems and also watch out for any typos, because what are you going to do with typos if you can't match them? So in conclusion, we defined 2 new naming conventions which haven't existed before. We developed an accurate program which can convert these names. We created an expandable dictionary for German and Latin, but also for synonyms. And we created 60 new OR name stems based on the convention. For any further development, there are a few special cases which could be interesting to improve. The removal of dates and the detection of typos, we talked about it in the last slide. And there is the idea of using the ground truth dataset to match new names to. So instead of directly converting them, you would first look if the name matches to an already converted name in the ground truth dataset, and then you would just use that instead of actually converting it first. So the take-home message would be that structure naming in radiation therapy has to be standardized. And if I have piqued your interest in medical physics, there are a lot of lectures at ETH, but also at UZH, but I haven't listed the UZH lectures. For bachelor, we have an introductory lecture, which is given by the supervisor of my thesis. The first 2 in the master are also given by my supervisor, and the others are given by other really good lecturers, so you will never get bored if you want to learn about medical physics. And yes, thank you for listening, and I'm now open to questions.
Any questions?
Yes?
How did you know, for all the radiation values and things, how did you know, you said you were using
Centigrade.
and millimeters, how did you know where the comma is kind of, it's just not a very high dosage?
So a single dose to a target is somewhere between 50 and 60 gray, generally. And in treatment planning, ironically, the units we use are actually centigrade and millimeters. So it's the first thing we would choose would be centigrade and millimeters. And in the code, you have to look at different special cases. So there were a lot of ones which you had like 6,900, but you also had 60.1. So you just have to write a code that that knows that if there's a point, and depending on how many characters are before or after, that it knows it's either an expansion or it's a dose. It's just you have to look at I looked at so much data. At some point you see a pattern of what usually happens during treatment planning, and I also talked to different medical physicists on how they do it, and then this helped to narrow down which special cases the code has to check and which one is just a normal case, which would be like 6,900. That's normally the way they label it, but there are always special cases. Yes?
How does the code sort of detect the patterns? What is the...
So it's quite just on a logical basis. So basically you look at how we know what we want to have for a name, so we have the convention, so we know which parts we have to identify, so every step is a single function, and the code will look at the string, and for example for the target volumes it will try to see is there any version of PTV which is in the name. So you can have like an uppercase P and then all small, but you could also have all uppercase or all lowercase. So you just have to tell the code, hey, I want to find PTV in any shape or form, and if it finds it, it will then decide, yes, it's PTV or any other target volume. And for the name stems with the OR, it's the same. You can look for any variation or any similarity. So sometimes the code works in mathematical similarities, so you look at the distance between the two words, and the closer the distance is, the higher the probability is that that's the match that has to be made to identify the name stem.
What kind of distance were you using?
So we used the Levenstein or the Stirn distance, but we also sometimes we just use simple string matching, like literally you ask PTV equals test, and you figure out if PTV is in it. It depends a bit on the thing you want to match. If you want to match target volumes, you can easily just look up if a version of PTV is in it, because there's not really 100 ways to write PTV. But if you have an actual name, then you have to look at how far away these two words are, and the closer they are, the more likely it is that it's going to match. But then you also add like the synonyms, which you first have to translate into like its standard name. So if the code finds a problem, if every distance for every word is so big that it doesn't find anything, it will then go into the dictionary and just check, is this a word which is in English, in German, or a synonym? And if it finds a match there, again with the same distance calculation, then it will redo the convention and conversion with that newfound translation. Yes?
So is or how far-reaching is your project now? So do they just want to apply it now in this research group, or is the goal to standardize it for all students?
So the first step would be to apply to the research group, so to the 40 years of data that they have. And the next step would be to write a paper, to then publish it and to make it available for all research groups, in the hope that we can, over every English-speaking research group, that they can use a standardized convention. And the group at PSI hopes that they could use mine, but who knows, maybe there will be another one in a few years' time, but yes, that's the goal. Well, thanks.